Good morning. It is 10 o'clock Central Standard Time here at the Environmental Education Center in Seagoville, Texas. We want to say a special welcome to Martha Turner Riley, the Mighty Rams, and we hope you enjoy the program. Now, if anybody is watching the program and they have not signed up, if you would, please go to www.tiny.cc/EEC, register and sign up. We need this for our attendance records. Today, we're going to do the weather and the water cycle. During this virtual field trip, students will discover that there are recognizable patterns in the natural world among the sun, earth, and moon system. Students will observe weather conditions and be able to describe the water cycle. Mr. Monroe, he is going to do a program called Changes in the Weather, and that's really a good program for right now here in Texas. Ms. Nash will talk about the water cycle. Ms. Fuller will talk about the Beaufort scale. Ms. Ramirez will tell you about a wind investigation, and we have a guest meteorologist, Mr. Wesley, today. During this program, you cannot verbally ask us a question, but you can go to www.tiny.cc/EEC /question /answer and send in your question. We'll do our best to answer them during the program. If not, we'll send the answer to your teacher. And now I'm going to stop sharing my screen. And we're going to have Mr. Monroe tell us all about the changes in the weather.
Good morning, students. My name is Mr. Monroe, and my topic on your virtual field trip today is to look at changes in the weather. Well, we know definitely weather never stays the same, does it? It's constantly changing. And, predicting and forecasting those changes are very important to us in our everyday lives. Now, listen, I've often made the statement that weather controls our lives. It tells us what we can wear on certain days. It tells us what kind of activities we can do. And so predicting and forecasting those changes in the weather is very, very important, even for our own safety. Now listen, there are very special scientists that we call meteorologists. And one of the major jobs that they have is to predict and forecast the weather. And they do this by measuring and collecting data about certain weather conditions that will enable them to predict and forecast the weather to the best of their ability. Now, to really get an understanding about weather, what is weather? Well, it's the day-to-day conditions in our atmosphere that affect our surface at a particular time and a particular place. And see, that means that it's going to constantly be changing, and it may not be the same in one area as it might be in another. For example, where I was born and raised, definitely it would be different there today than it is here today in North Texas. Now, when we talk about the atmosphere, we're talking about the air bubble that surrounds our planet. And there are three major components that make our weather. The sun, which is the ultimate source of energy for our weather patterns, the water that is on the surface of our planet and located in our atmosphere, because water can be found in that air bubble that surrounds our planet. Now, the other component is the air that surrounds us. Of course, we can't see it. The only time we feel it is when it's moving. And there's a name we give to air that is moving. We call it wind. All of those three components, guess what? They make weather. And meteorologists, remember, they're special scientists that study weather in our atmosphere. They use instruments to measure some of those components and to record data from some of those components, and they compile it, and they come up with predictions and forecasting the weather. So listen, I'm going to show and share some of these instruments with you, and then we'll figure out whether you guys can be good weathermen or good meteorologists, okay? Starting with the heating of our planet. Our planet is in a spherical shape, so it receives a lot of uneven heating. There's an instrument that meteorologists use to measure how hot or cold the air is. It is called a thermometer. And a thermometer is used to measure the temperature of the air or how hot or cold the air is around that instrument. Inside that instrument, there's a tube. And that tube has a fluid in it. It's usually colored red. And long ago, they used a fluid. It was mercury. But they found out mercury can be kind of dangerous. It's toxic. So nowadays, they use alcohol or an alcohol-based solution. Now, with the thermometer, you might find two sets of numbers, and they represent two different types of measuring systems. For example, this thermometer on this side, we see a C. That stands for Celsius. So these numbers represent metric units of measurement in the form of Celsius. On this side, we see an F for Fahrenheit, and this side is the customary measurement for Fahrenheit. And in the United States, in America, we usually or normally use the customary measurement system. Countries and located in Europe and around the world, they may use the metric. And to show you how that really works, I have a demonstration model here. This demonstration model, that fluid has a tendency to expand whenever it's heated up. So that would make the fluid in the tube, it would make it go up. Now, if it cools down, guess what the fluid's going to do? It's going to go down. So that's how a thermometer works. Now, that's about how hot or cold the air is. And we know it's being heated up by the sun. The other component that I want to talk briefly about is the water that's found on our planet, either on the surface of our planet or located in our atmosphere. The amazing thing about water, it can be found in our atmosphere in the three natural states of matter. It can be a liquid, it can be a solid, or it can be a gas, and all of those can be found in our atmosphere. What we're concerned with, or what meteorologists are concerned with, is how much rainfall we can receive or we do receive. And they use an instrument called a rain gauge. Now, this little portable weather station, if I was to place it out today, it does have a rain gauge on it, this tube right here. Now, this tube would collect the rain or the precipitation that's falling, and it would settle in the bottom, and it eventually would rise to one of these measurements. On one side, we have measurements in inches. That's the customary. On this side, we have it in centimeters, and that's the metric. But that's an example of a rain gauge, okay? It measures the amount of precipitation that we receive. The other component that meteorologists would be looking at is wind direction. Now, when we talk about wind direction, that's very important because it can also indicate how hot or cold the air might be. For example, if we know the wind's coming from the south, we know southern winds usually are coming from the area around the equator. That usually indicates that that's going to be warm air. And then sometimes the wind will come from the north. And when that happens, we know that that air or that wind is going to be cool or it's going to be cold. And that wind vane will help us decide which way the wind is blowing from. Here I have a model of a wind vane, and we see that it has abbreviations: E for east, N for north, W for west, S for south. And I kind of have an idea that that's north. And to be sure that that would be north, there's an instrument you might use. It's called a compass, right? But we don't need that today. If the wind is coming from the north, this arrow is going to turn this direction using the rudder. And it's going to show us that the wind is coming from the north. That wind would be most likely cool or cold, okay? So that's how a wind vane works. And then we kind of need to know how strong or how fast the wind is blowing. So there's another instrument that meteorologists would use. It's called an anemometer. And that anemometer has little cups on it. This is just a model right here. And it would be setting out in the open with no obstructions around it. And as the wind blows, the wind would catch in the cups and it would spin like this. it would be attracted or attached to a electronic device that would calculate how fast the wind is blowing. And in miles per hour, basically, is what it's going to measure it in. And I can remember one day it was predicted our wind would be at a sustained speed of 40 miles per hour. That's a pretty strong wind. And that would well, you could step out, probably would see the trees doing a tree dance, weaving back and forth, dancing in the wind. That's what I call it, okay? And there are other instruments. For example, at a small airport, you might see something called a windsock. Oh, about 2 or 3 weeks ago, I went to buy a windsock, and most of the people in the store didn't know what a windsock was. And one young man, he asked me, he said, well, mister, is that a special sock that you would put on your feet? And I had to tell him, I said, no, it's an instrument that would be used to tell observers how strong the wind is and what direction the wind is blowing from. I have a windsock right here, and I'm going to shift my camera just a little bit that way. And I'm going to furnish a little wind by using a blower. And let's see if this thing will work. There she goes. That's a windsock. That's how it works, okay? And look what happens if the wind dies down. The windsock drops back down the same way with a flag. If it drops down and it's not moving, that tells us it's very calm. And at a small airport, if a small airplane was taking off or beginning to land and they saw the windsock like this, they would feel pretty good thinking that, hey, we won't have any problem with the wind today. The wind is calm. But on the other hand, if it's straight out like that, could be problems for that small airplane. You know, meteorologists use a variety of other instruments, such as weather balloons that they release into the atmosphere that has a box with instruments that will collect data and send it back down to that meteorologist so that he can chart it on a map. Or they have radar called Doppler radar, where they can track storms. And the radar has gotten so sophisticated now that they can even determine whether there's a vortex in a storm called a tornado. So we have come a long ways predicting and forecasting extreme and dangerous weather. You know, they also have satellites that revolve around our planet or orbit around our planet, like so, taking pictures of cloud formations and weather patterns that are going on, and they send those pictures and data back to those meteorologists. And then a very important tool that they really monitor weather changes is a weather map. And there's several different types of weather map, but this one is a surface weather map, and it's showing different symbols that meteorologists have put on a weather map indicating different types of weather patterns in which way they're going. Now, as far as weather patterns are concerned, most of the time, our weather patterns in North America or in the continental USA, they move from the west to the east. Every once in a while, we get a little something different. In fact, a little over a week ago, we had a weather pattern that came from way up north around the polar caps. It was called a polar vortex that really did cause some problems for Texas. In fact, the whole state of Texas suffered behind that particular pattern, okay? But most of the time, our patterns come from the west to the east. And I'll tell you a little secret. That polar vortex, they predicted it was coming. They knew that we were going to get some cold, cold temperatures. I don't think they realized how cold it was going to get all the way down to the Gulf of Mexico. So weather is constantly changing, and meteorologists are constantly trying to use these instruments and whatever data they can collect to predict and forecast those weather changes. Now, if any of you have any questions, I'm going to turn it back over to Dr. Gorman, and maybe he can answer those questions for you. You guys have a good day.
Thank you, Mr. Monroe. And we do have a question. Who invented the windsock? I was thinking about Woodstock, but you guys don't know that. Actually, the actual inventor is unknown, but the Japanese have used the windsock for centuries. Now, originally, it was put up outside. Now, at that time, they didn't have hospitals. So babies were born in the house, okay? So when a baby boy was born, the family would put up a windsock. It was made out of silk and out of paper. And that indicated that a baby boy had been born. Now, some smart guy came along and saw one day that the windsock was blowing up a little bit, and the next day it was blowing up more. And so he was able to kind of invent the windsock, I'm sorry, as we use it. So it probably came from the Japanese. And now Miss Nash is going to tell us all about the water cycle.
Hello, welcome to my classroom. And I know you've heard about the water cycle before. It's a cycle. That means it goes around and around. It repeats itself. The water we have now, same water that the dinosaurs were drinking. So just remember that. Now, today is a great day to be thinking about the water cycle because it's happening right outside your window. Okay. I've been watching it rain and watching the puddles form. So let's look at a few more pictures and then we can talk about what we could do to just really explore it on our own. So we've all seen all the diagrams, basic steps. So we have precipitation like we're having now, rain or snow or sleet, and that rain or whatever accumulates either in the ground or on top of the ground, and then the heat of the sun drives evaporation. Plants suck up water to their roots and their leaves transpire or give off a lot of water vapor also. All that water vapor goes up into the sky where it's cold, and that water vapor condenses into a cloud of the tiny water droplets. And then if there are enough of them, they can fall down in precipitation and so on. It can be more complicated. Okay, we've got ice and snow, they melt. They can also sublimate or go directly from ice to a cloud. We have different between lake, ocean water, etc. So if you start with our cloud, we get all different kinds of precipitation. We've got snow like we saw recently, we've got rain, we've got ice, hail, and we've got fog, which is kind of a cloud on the ground. And transpiration is one of my favorite things that we don't think about very much. And that's when plants suck up that water from the ground through their roots, goes up to the stem, out to the leaves. And the leaves actually give off water vapor. And then in the Amazon, this is a picture of the Amazon, it makes its own clouds. So the trees make water vapor, they give off water vapor, it condenses and rains back down. Pretty amazing. Isn't that amazing? So here's another picture of the way the trees are making their own rain through transpiration. So the sun will evaporate that water off. Heat from the sun will cause that water to change into water vapor and evaporate. Most of it's coming from the ocean. So since most of our planet is ocean, most of the evaporation is coming from the ocean. Now, it's not salty because the salt is left behind in the ocean. So the vapor that comes up doesn't have any salt, even though it came from salt water. And it goes back to clouds. So it's that cycle. Okay, back again. Now, today is a great day to go out and observe that water cycle in action. So I see the clouds, heavy kind of dark gray clouds, and rain falling out of them. And one thing I noticed is there are puddles on the sidewalk that are going to stay there. And then the puddles in the ground will gradually go down into the ground. Those puddles on the sidewalk will evaporate really quickly. Now, transpiration. So I like that. And you can prove to yourself that this is happening by just taking some leaves and putting it in a plastic bag and sealing it up. I did this on Sunday yesterday. And already I see little drops of water in here. Okay? It's coming from these leaves. They're giving it off. Okay? They're giving off that water vapor. It's condensing on the plastic bag. Now, condensation, let's look at that. I've got a funny little bottle thing here, and it's a plastic bottle with this funny thing on top. And if I squeeze it, it pushes more air into the bottle. If I squeeze and squeeze and squeeze, and it's like, it gets harder and harder to squeeze, it's getting full in there, full of air. And that air pressure is making it hot in here. So it's heating it up. And then when I release the pressure, it's going to cool off. And the vapor in here will condense into a cloud. Watch. Wow, a cloud in a bottle. Isn't that cool? So a little cloud in a bottle, a condensation. Had enough bottles, enough to go. I can make a big cloud and it can rain. So it's a great day to look at the rain, observe the rain, look out the window and see where it's going. Is it making a puddle, it's soaking into the ground, the plants are going to need it. So thank you. And if you have any questions, you can ask Dr. Gore.
Thank you, Ms. Nash. And a question that came in is, how long is water involved, or drop of water involved in the water cycle? Okay, various answers to that. Scientists have discovered that if a drop of water is in the ocean, for it to go through the full water cycle and get back into the ocean could take as long as 3,000 years. Now, if that drop of water was in the atmosphere and it fell to the earth and was evaporated and went back in there, that could happen in as short as 9 days. But now this is the big one. If a drop of water fell into the polar ice cap and froze, it could stay in there for hundreds of thousands of years before it evaporated and went through the cycle again. I hope that answered your question for you. Now, Ms. Fuller is going to tell us about the Beaufort scale.
Good morning, boys and girls. We're going to talk about scales today. And I have with me my little lab assistant. This is Spring, the ball python. And Spring is covered in a kind of scale. And the scale is very important because it keeps Spring from dehydrating. It keeps her from scratching her skin. And look at her tummy. She's got big rectangular scales on her tummy that helps her slither, and she also has scales on her eyes because she doesn't have any eyelids. Let me put her down because she's kind of wiggly. Another kind of scale is one that we measure things with. Your teacher may have one of these scales in her science lab. It's an O-House scale, and this is how we mass things in science. Well, still another type of scale is one that we measure things like the strength or compare things. For example, if you know about the pH scale, you know that it compares acidity and alkalinity. Let's look at the Beaufort scale. Whoops, that's the wrong one. I'm going to share my screen with you. And let me pull our little presentation down. So what does the Beaufort scale measure? It's a relating scale. It relates wind speed to observed conditions on sea or on land. And that man is in about Beaufort scale 12. The wind is so strong, he can't even stand up. Now, you may be familiar with the Richter scale. The Richter scale measures the intensity of earthquakes. Now, here's a picture of Francis Beaufort. He was an Irish scientist. He was an admiral in the United Kingdom's Royal Navy, and he decided that there needed to be a way of having a comparative scale for the sailors. They didn't have the type of technology we have now. They didn't have anemometers and GPS and Wi-Fi and all those wonderful things we use now. So he thought this scale would help the sailors as they went through the sea. This is back when ships didn't have engines. They were being driven by sails, and they had to have wind in order to drive the ship. So that's a picture of wind at sea. The picture on the right shows a family out flying a kite. And as you know, it takes wind to to fly a kite on land. So the Beaufort scale has 12 steps. The first one is perfectly calm, just the slightest little breeze. The Beaufort scale force 2 is one, and it's described in what the sea looks like. So on a Beaufort scale 2, the waves are about 2 to 3 0.2 or 0.3 meters high, very, very low, like a foot high, small wavelets. And the crests look glassy and they don't break. Okay, Beaufort scale force 9, which is closer to the big part of the scale, the winds are at 41 to 47 knots. The waves are 7 to 10 meters. That's over 30 feet. That would be taller than my house. High waves, dense streaks of foam. The crests topple, tumble, and roll over. And there's so much spray in the air, it may even affect the visibility. Beaufort scale force 12 is the highest rating on the Beaufort scale. And the wind speed is at 73 miles per hour or 64 knots. The sea is completely white with driving spray. The visibility is seriously affected. The air is full of foam. It's going to be crashing over the top of the ship. This is a very serious wind condition. Now, once you get to 74 miles per hour, we come up to hurricanes. Hurricane force winds begin at 74 miles per hour. And this is when you switch over to a different kind of scale, the Saffir-Simpson scale. And let's talk about women in science in wind right now. And Juliana Kanga, she's a current woman scientist, and she's involved in wind energy, and she lives in Kenya, Africa. All right, so let me stop sharing my screen. And if you have any questions about wind, especially wind at sea that's being measured by the Beaufort scale, Dr. Gorman served in the Navy for many years and was at sea, and he can answer any questions you have about wind at sea. Have a delightful day.
Thank you, Ms. Fuller. And yes, I did spend a lot of time at sea, and I was in a hurricane in the South China Sea. I believe in that part of the world, they call it a typhoon. I believe that's correct, but it was a hurricane. And yes, many of the sailors and Marines on that ship got very seasick, even though it was a very large ship. It was quite an experience. The question that came in though, can you name another planet that has wind? And yes, just last week we were able to listen to the Mars rover, and they sent back messages, and part of them had the sound of the wind blowing. Many of the scientists were very disappointed. They thought it would have a different sound up there, but it didn't. It sounded just like the wind does here. And now Ms. Ramirez is going to tell you about investigating the wind.
Hello, my name is Ms. Ramirez, and in this segment, we're going to be learning about wind, and we're going to complete a wind investigation. So I'm going to share my screen with you guys, and it might take just a second to get that going. But while we're waiting for that, be thinking about what is wind. So how can you define that? So some essential questions for you guys. Hopefully by the end of this lesson, you guys will be able to answer these two questions. So keep these questions in mind. The first question is, what is wind? And the second question is, does water heat up and cool down slower or faster than land? And you should be able to explain that by the end of this presentation. Now, since we're going to start off learning about wind today, and y'all aren't able to visit us here at the center, I actually took some video of some of our windiest days that we've had at the center. So make some observations as you watch the video and think about what tools can we use to measure wind, and how can you tell it was a windy day when this video was taken. So I'm going to play the video for you guys. Hopefully it plays. There it goes. So we know that gases move from high pressure area to low pressure areas. And the bigger the difference between those pressure areas, the more rush of air we will feel. And that rush of air is simply known as wind. And wind is a part of weather that we experience pretty much all the time. And again, it's caused by differences in air pressure differences and also differences in temperature. So as you guys were watching the little video, we knew it was a windy day because we saw the flags blowing, we saw the wind blowing the water across the lake, we saw the windsock moving, we saw the tree leaves rustling in the wind. So even though y'all weren't able to visit us, there are definitely clues in the video that we've experienced some windy days. So that's an intro to wind. Now, I actually did a wind investigation, and the way I set up this investigation, we were trying to figure out what effect does land and water have on temperature differences. So I have two beakers here. One beaker is filled with water, and that represents bodies of water, for example, an ocean. And then I have another beaker here on the right that's filled with soil, and that's going to represent temperature on land. So the first thing I did is I put both beakers inside my classroom. I put a thermometer in them, and I took the temperature of each. So go ahead and really quickly see if you can figure out what the temperature readings are in Fahrenheit and Celsius, and then we'll move on to our next part of the investigation. And then also be thinking about what do you think will happen to the temperature of each beaker when I place them outside in direct sunlight? So inside the classroom, you can see that they're about the same temperature inside, and that's about 66 degrees Fahrenheit. So they're starting off at the same temperature. This is going to be kind of like our control, would be the classroom temperature. Now I'm going to place them outside in direct sunlight. So make your hypothesis. What do you think is going to happen to the temperature of each beaker and why? So when I place them both outside in direct sunlight, go ahead and make your observations about what you guys noticed about the temperature. We have the land beaker on the left, and then on the right, we have our water beaker. So make your observations, make your temperature recordings. Now the land beaker, we can see right away that the temperature rose rather quickly. So it got up to 80 degrees Fahrenheit in direct sunlight. So the temperature rose quick. Take a look though at the beaker with the water. The beaker with the water didn't raise its temperature that much. So remember, they both started out at about 66 degrees Fahrenheit. So now in the sunlight, our land is about 80 and our water only made it up to about 74. So what this first part of the experience of the investigation tells us is that land will heat up faster than bodies of water. And we can see that with our temperature readings from our beakers. Now, this actually simulates what we call a sea breeze. So think about the coastal areas. Cooler air from the sea will blow onto the land during the daytime. And as you can see from our beakers, water is cooler in this part of our experiment compared to the land. Now I'm going to put both of these beakers in a shady area. Now make your predictions. What do you think is going to happen to the temperatures of each and why? So here they are in the shade. And again, make your observations. What do you guys notice about what happened to the temperatures? And so we can see the land this time dropped rather drastically again. It dropped to 66 degrees Fahrenheit, so to what it was in my classroom that day. And then take a look at our water. It actually stayed the same temperature. It stayed about 74 degrees Fahrenheit. So what this tells us is that the land will warm up faster, and it will also cool down faster compared to our water. So let's take a look at what this means in real life applications, especially for those living in the coastal areas. So this represents a nighttime scenario since it's in the shade. The land, again, cools down faster than bodies of water. So it went all the way down to 66 versus the land versus the water that stayed at the 74. So during the nighttime, coastal areas will experience what's called a land breeze. So the cooler air from the land will blow onto the sea. And that's what we refer to as a land breeze during the nighttime. So overall, bodies of water will heat up and cool down more slowly than the land. And then here's some other real life examples. Now, not only does this affect coastal areas near oceans, but also the same effect is common along other bodies of water like lakes. So here we have a diagram of a lake. We can see the warmer land inland and then the cooler coastal area or the cooler lake areas over here in this. And then here's another example with our coastal areas. The sea breeze effect is what we just investigated. So we have our cooler temperatures during the daytime for our coastal areas and then the warmer inland areas. Not only does water affect temperature, but also landform. So look at this diagram here and see if you guys can describe what's happening as far as temperature when it comes to temperature in the valley versus temperature at the top of the mountains, and how that can also create breezes as well. So the different heating and cooling rates of land and water and even landforms will affect our daily and our seasonal temperatures. So to wrap it all together, I have a quick challenge question for you guys. I would like to see if y'all can research a weather phenomenon with extreme winds. Think about what causes that weather and then where does it commonly occur and how does it affect people. So to give you guys kind of like a little help, I have some interesting pictures of some weather phenomena with extreme winds. These are just some that I found online, but you can research your own and see if you can find other cool phenomena with winds as well. Most notably, downburst winds and straight line winds, tornadoes. Those are probably more that are going to affect us here in Texas, but then other parts of the US will experience other weird extreme weather as well. So I'm going to go ahead and stop our screen share, and that's all I have for you guys today on winds. And we're going to pass it back to Dr. Gorman, and he's going to answer any questions.
Thank you, Ms. Ramirez. And the question came in, what are the speeds, wind speeds of a tornado? An F3 tornado, the wind blows 158 through 206 miles per hour. An F4, 207 through 260 miles per hour. And an F5, 261 through 318 miles per hour. That's the one that really does a lot of damage. I'm not sure which one we had in the Dallas area a year or so ago, but it did destroy several of our schools. Now, Mr. Broughton is going to introduce our guest speaker, Mr. Wesley, and he's going to tell you what it takes to be a meteorologist.
Thank you, Dr. Gorman. Yes, Mr. Wesley is a meteorologist for the Texas Commission on Environmental Quality. So there you can see their website, and they study the air, the land, and the water there. And you also study the air, land, and water in fourth grade. So this might be a good website to visit if you ever need to do some research on air, land, and water quality in Texas. And that website is tceq.texas.gov. And then part of TCEQ is Take Care of Texas, which is their website is takecareoftexas.org. And they also study water, the air, the land, and how to keep everything clean here in Texas. There's resources for kids, resources for teachers. Most of these resources, if not all, are free to use. And now we're going to meet Mr. Wesley, and he's going to tell you what a meteorologist does.
Hi, my name is Wesley, and I'm a meteorologist with the Texas Commission on Environmental Quality, but we call it the TCEQ for short. The TCEQ is a state agency that protects our environment and makes sure our air, water, and land is protected from pollutants. We also teach Texans about how they can help keep Texas's environment clean. I'm a meteorologist, but you might have heard the job called a weatherman. A meteorologist is a scientist who studies the weather and makes a forecast so we know what the weather will be in the future, which could be the weather tomorrow or the weather in a month. I'm a little different than the weatherman you see on TV. I track weather to study how it will affect our environment, as well as track how it affects air pollution. Sometimes pollutants can make our air dirty, which is especially important to know if you have asthma or other health problems. I make sure Texans know when the air is safe and clean to play outside. We use a colored chart to show how clean the air is. Green is the best and purple is the worst. Typically, we see orange ozone action days in the summertime when there's lots of sunshine and winds are light. They're also more common in big cities where there are more cars. To study the weather, I use weather measurements. Those are taken by air monitoring instruments and by air investigators. They work all across Texas, taking data with handheld monitors, air monitoring vehicles, and stationary air monitors. Their machines can sense lots of different things about the air that we can't see with just our eyes. They can tell us the temperature, pressure, humidity, and different types of invisible particles that are floating in our air. I use the information they gather to decide what that means for the weather and predict the amount of pollution that might be in the air. You can even monitor the weather yourself by using thermometers, rain gauges, anemometers, wind vanes, barometers, and hygrometers. Texas weather is very unique and special. Texas is very large, which means we have different types of weather across the state, even in a single day. It could be snowing in Amarillo while people in Corpus Christi are playing at the beach. In Texas, we have beaches and mountains, plains and hills, swamps and deserts, forests, and, well, you get the picture. Because of these different types of land, we see lots of different types of weather. Some of the types of weather we see in Texas are thunderstorms, hurricanes, tornadoes, snow, and fog. Texas has several different types of weather patterns that we see year after year in our state. Some common weather patterns we see are cold fronts, which are large areas of cold air that move across the state. Cold fronts cause some of the most interesting weather events that happen in Texas. When a cold front comes through, it's pushing the warm ocean air back out over the Gulf of Mexico and brings in the cold mountain air from the north. It happens all across the state as the cold front moves. This is why you might wear shorts one day, but the next day you might need a jacket. Another interesting weather event we see in Texas is hurricanes. They are very interesting to watch because we, as meteorologists, try to figure out where they are going to go. This is important so we can know whether or not it will cause problems for people who live close to the coast of Texas. It is important to know the difference between weather and climate. Weather is what is happening today and the next several days. Climate is the average weather over a longer period of time, like months and years. For example, even if the weather is rainy today, if it is the only time it has rained in the last 6 months, the overall climate during this time period would be dry. At the TCEQ, we track both weather and climate, since they are both very important. Thanks for taking the time to learn more about how the TCEQ helps you take care of Texas.
And I would like to thank the Texas Commission on Environmental Quality and especially Mr. Wesley for taking the time to work with us on this virtual field trip. And now, students, you should know quite a bit about weather and even how to use that information to become a meteorologist when you grow up if you're interested in the weather. I'm going to stop sharing my screen here and turn things back over to Dr. Gorman to answer any questions and wrap this trip up.
Thank you so much, Mr. Broughton. That was very interesting. We do have a question. How long does it take to become a meteorologist? It takes 4 years at a certified college or university. You'll get a Bachelor of Science degree in meteorology or atmospheric sciences. Now, some teaching positions require research or management positions require a master's degree or a PhD. Okay. Now I'm going to share my screen. During this virtual field trip, students discovered that there are recognizable patterns in the natural world among the sun, earth, and moon system. Students observed weather conditions and were able to describe the water cycle. Mr. Monroe talked to you about changes in weather. Ms. Nash did the water cycle. Ms. Fuller, the Beaufort scale. Wind investigation by Ms. Ramirez. And we want to thank you for joining us. Tell us how we did. If you go, teachers, if you go online to www.tiny.cc/EEC feedback and send us information about how we did the programs. Thank you for joining us. You have a great day. Most importantly, a great life.